We're going to do a three-part series now on sedimentary rocks. In our online textbook, which you can find at opengeology.org, it is chapter 5.3. And it's in the same chapter where weathering and erosion occurs, because those are the processes that are breaking down rocks into sediments. And now here, we're going to take those sediments, we're going to transport them, we're going to deposit them, and we're going to lithify them into sedimentary rocks. As an important concept here is that this is the history book of our planet, these sedimentary rocks, and the reason for their study is that they record past events. You can read the sediments, understand the carrying capacity of fluids, the depositional of environments of fluids, interpreting them. I'm going to put the word here, interpretation, as well. To look backwards in time, interpretation. To look backwards in time to understand this planet. This is also where fossils are occurring. And it's also where oil, natural gas, hydrocarbons, coal are all coming from sedimentary rocks. So these are the significances within this topic. We're just going to kind of dive right in here and do a series of lists in this lecture, the next lecture, and the next. And to start it off, we're just going to go with the 4 types of sedimentary rocks. And I'm going to get through 3 of them in this lecture, and we'll save clastic sedimentary rocks for its own lecture because it's a big topic. So we have 4 types of sedimentary rocks. Number 1 is biochemical. These are, we could say, maybe we shouldn't say organic, but these are made by organisms as they make their body parts. This is shell and coral turning to limestone and chert. So we got to get some of those notes here in. And for our definition for biochemical, the key here is that it's biology and the organism itself is secreting a mineral. So let's say organism extracts, it's either calcium or silicon for the rock types that we're talking about today from water to make their body parts. All right, to make their bodies. And the types of we're thinking here are, these are shells, this is coral reefs, and this is plankton. These materials, these organisms, they die. And when they die, their body parts accumulate on the ocean floor. So we'll say accumulation, we'll say of body parts. It could be a lake floor technically, but oftentimes it's ocean floor. They just settle to the bottom, and then compaction pushes those body parts closer together, and fluids will move through them and will cement them together. And that's how we get this rock. Within this biochemical family, there's 2 types of rock I want you to know. The first is limestone. And within limestone, there's actually going to be 3 varieties, 1, 2, and 3. And it's going to be fossiliferous limestone. There's going to be micrite limestone. And then finally, there's going to be chalk, which is its own name. It doesn't have the word limestone at the end, where fossiliferous and micrite will. And all 3 of these are slightly different in their appearance. Let's see, here we go. Fossiliferous limestone. This is a near shore environment. This is where organisms are living in like coral reefs. I want you to think near shore and more reef-like environments to produce these fossiliferous limestones. Micrite limestones, they look a little different. This I want you to associate with deep marine, far from shorelines. There's going to be more plankton involved in the accumulation process here, where the reef is more shells and corals. With respect to deep marine, I also want you to think of the word fine-grained. In the deep marine environment, there's not big currents to carry things, whereas in the near shore, there's waves. And so fossiliferous limestones tend to have bigger particles, bigger shell pieces visible, and the micrite limestones are much more fine-grained. Now, chalk has just been less compacted. It's white, and it often is made of mostly plankton. Let me put in some pictures of these rocks. You can always, of course, look them up on the internet to see other kinds of pictures, but here's like a general picture of the environment in a nearshore environment with coral reefs that then later, like this is like an outcrop driving on a highway in Texas, you can see all these limestone outcrops forming. And back in time, if we were to read the history book of Earth, the landscape that we should predict is one of this blue, beautiful Caribbean coral reef. With respect to now the actual rock, this lecture ends up being fairly image heavy. Here is a micrite on the left. Micrite, oh, come on, micrite. And then here on the other side, this is where we have the fossiliferous. And you can see the different textures, how fine grained the micrite is. And then in the fossiliferous, you can see examples of snail shells and different corals. And then finally, for the last picture of limestones, it is one of the White Cliffs of Dover. And so these white cliffs here are made of chalk, which is a type of limestone. Now, within this category of biochemical, there's another type of rock that has a different composition, and it is chert. Oh, that reminds me of something. Let me go back up and say something about limestone. The mineral that makes up limestone is calcite. And the chemical formula for calcite is CaCO3. We've talked a lot about carbon dioxide so far this semester, and you can see how CO2 fits in that chemical formula for calcite. We've talked about calcite with respect to caves earlier this semester. Well, the reason why I bring up the composition is because chert is made of quartz, which has the chemical formula SiO2. And it is produced when plankton die, but it's plankton whose body parts are made of silica. That's another way to say SiO2 is silica. So we're going to say plankton made of silica. It's a different type of plankton than the calcite planktons, but they definitely happen in a lot of different places in the ocean. Those will die, they'll fall to the ocean floor, usually in the deep marine environment. And so chert is also, so that says deep marine, even though you can't see that. Deep marine, fine grained. And what I would like you to, some other things about chert that I'd like you to know is that it's incredibly hard. It's erosion resistant, and it breaks with something called conchoidal fracture. These things might not seem to make much importance to you, but it's hard, which means it doesn't erode very readily. And conchoidal fracture has actually allowed it to be a very important resource throughout human history because it can be used to make things like arrowheads and spear points, which is what I'm drawing right here. So that's one of the places where you have probably seen chert in your life. To see, here's a picture of chert, like not as an arrowhead, but these fragments that are sitting on the ground, right? There's a fragment, there's a fragment, there's a fragment. These are actually archaeological, from an archaeological dig where some human was making tools and weapons from these. But it shows the conchoidal fracture and the beautiful colors. When chert is red, it is called jasper. And when chert is black, it is called flint. All right. Now, next up, so what do we have here? We have limestone. Oh boy, I did a 1 here for biochemical. I didn't put a number on limestone, and I put a number on chert. So I'm going to scribble out that, and I'm going to put number 2. The second family of the types of rocks is organic, and we have already spent time this semester talking about our organic rocks. You remember our organic sedimentary rocks? You remember? You probably, this is the coal family. And what we've talked about with coals is that there's an accumulation of organic material, usually in some kind of swampy environment. So it's a swampy environment, ferns and grasses and trees and reeds. They are accumulated in this environment. They're not breaking down, they're buried and compacted. So it's swampy environment, and then accumulation, and then burial, and then compaction. That's going to be our steps to making coal. And within this coal, it goes from peat, right, to lignite, to bituminous, to anthracite. And the reason why I'm going through this fast right now is we've already spent an entire lecture talking about this when we were back on hydrocarbons and the energy transition. Just as a yeah, you can go back to that lecture if you'd like to. Now, the third family of sedimentary rocks is called chemical. the chemical family. And the chemical family is very similar to the biochemical family, except for, of course, there's no bio here. And instead, I want you to think of chemical. This equals, at least in this case, we're going to call these the evaporative rocks. And so there is precipitation, the process. This is how salt forms, and gypsum and travertine. Those are the rocks we're going to get to. But what I want to show you, let's just start off with this picture. This is a picture from, I think this is maybe Death Valley in California. And there's a lake that sits in this basin. When it fills up with water, all this salt dissolves inside of it. But when the water evaporates, the salt then precipitates from solution to create a rock that's left behind. And that's what this family of rock are. And so let's say next to this picture, we're going to say precipitation. That means, in this case, crystallization of a mineral. So by precipitation from supersaturated waters. Supersaturated means very enriched in dissolved constituents. So precipitation from supersaturated H2O that may occur in response to evaporation. There's other ways you can do it, but evaporation is the biggest one. These are most commonly salt waters that are doing the evaporation. Now, in the picture here on the left, this is a salt water that's an actual saltwater lake, but many times it's also oceans. But we're going to say, so it's the evaporation of ocean salt waters, and it's also the evaporation of basin salt waters. And basin would be a lake like this one in Death Valley. All right, so there's 3 different types of this that I'd like to show you. It is going to be salt. Salt is also called halite, has the chemical formula of NaCl, and we have experience with this just because we use salt on all of our foods. It's going to be forming from the evaporation of salt water from oceans or from basins. Now, and this picture above is a great picture of how you can picture salt or halite. Okay. Gypsum is our second rock type that occurs in the sedimentary rock, are very common, and it also forms by evaporation, and it's evaporation of ocean water or saltwater basins, but here it's the waters are enriched in calcium and sulfur. That tends to be the ingredients that you need to create a rich sedimentary deposit of gypsum. And then our third and final rock for this category is travertine. It's a little different. This is going to be groundwater. It's going to be precipitation from groundwater, often from caves, and the mineral here is calcite. So it is not from saltwater ocean basins. It is not like halite. It is not like salt. When you picture this word travertine, you might actually picture a kitchen or a bathroom, because we use travertine in our building. But in the natural environment, before we've mined it, it is either in these cave deposits, right, as speleothems, or in this picture here, we're seeing hot springs. And the waters that are coming out of some hot spring are probably enriched in calcite, and then when they cool down, they can start to precipitate beautiful deposits of travertine. All right, next class, we're going to get into clastic, the 4th type of sedimentary rocks.